Hi again and welcome to the lecture course on Relativity and Cosmology Part 2. We are dealing with Chapter 9 and this is devoted to the classic test of general relativity. In 9.1 we have already discussed in detail the gravitational redshift or blue shift, also specialized it to the Schwarzschild metric, and now in this very important section 9.2 we deal with the motion of planets and also the propagation of light in the Schwarzschild spacetime. Now recall from lecture course 1, Schwarzschild spacetime is a spacetime, the empty spacetime outside a spherically symmetric mass with value m. So it's a vacuum solution. And the application we have in mind here is, of course, a solar system with the sun in the center and the planets moving around the sun. But of course, it can be applied to any other situation where you have one spherically symmetric body dominating and test bodies or light rays propagating around. Now, as you will learn here, we really need the Schwarzschild solution for describing the tests. It's no longer sufficient to just deal with the equivalence principle as we could do with the gravitational redshift. Let me write down the general spherically symmetric metric, ds squared, so without yet specializing it to Schwarzschild. So as we have seen in chapter 8, we have here one function of r. So this is a positive, the e to the nu of r, a positive function of r, t squared plus e to the lambda of r dr squared plus r squared e to the mu of r. And then we have the angles, d theta squared plus sine squared theta times d phi squared. I could have restricted already here to the Schwarzschild spacetime in, say, standard coordinates or in other coordinates, but it's convenient to keep it more general. Not because I want to use the other spacetimes in Schwarzschild, but we can use Schwarzschild spacetime in different coordinate systems. And so it's good to leave this freedom here. Now you could absorb the e to the mu into the r squared. That's certainly fine, but it's not needed. Now, if you recall what we did earlier, very early when we discussed geodesics, we could derive the geodesic equation of motion from a variational principle. So instead of really writing down the Christoffel symbols here and writing the geodesic equation of motion, well, this is what people have found out. It's a shortcut in the calculation to directly deal with the variational principle, because then you are on a higher level, at the level of the integrated version, and this will turn out to be quicker. So we recapitulate the variational principle, which we did in section 4.3, and also there were exercises at that time that you solved. And so the statement is that the geodesics can be found from the following variation. So we vary integral d lambda, and then we have the space-time metric g mu nu, dx mu over d lambda times dx nu over d lambda is 0. That's what we had. The original principle was here the square root of this, because we varied over the proper time. But as we showed then in the exercises, the same results follow from this, and because there's no square root here, it's simpler to do the calculation. Now, this here is, we call a certain Lagrange function, k. That's what you integrate over. And this dx mu over the parameter lambda, we abbreviate with the dot. No? So, and also others that we differentiate with respect to lambda. This is denoted by a dot. Now, this, of course, generalizes time derivatives. I mean, if we have the time-like case, so massive test bodies, then lambda is equal to the proper time, s, and from there we have, of course, that this is normalized to -1. So this is a constant. And for the light-like case, we have ds squared equal to 0, so there's no proper time. So lambda is just an affine parameter that runs along the light rays. And because this here is 0, we have k equals 0. So I will later divide the discussion into these two cases. Now, let us be more specific. If we have this, we have to insert here now the metric. No? We have here the G00, the G11, or I call GRR, and so on. And these are only diagonal elements of the metric. No? So from this here, we have that k. You just have to insert this here is minus e to the nu t dot squared, and this comes from this here. Then from the second term we have e to the lambda r dot squared, and then we have here plus from this r squared e to the mu theta dot squared plus sine squared theta times phi dot squared. So, and this is a Lagrange function par excellence. As in classical mechanics, it's a function that depends on q's and q dots. And you can use the standard formalism of varying in action and discussing the Euler-Lagrange equation. Now what you see here is that there two of the four variables play a distinguished role. And these two are the coordinate time t and the angle phi. Why? They occur here only in their differentiated version, in their dotted version, phi dot squared and t dot squared, but they do not explicitly appear as functions themselves. Phi and theta do not occur. And you know from classical mechanics that such variables are called cyclic variables. And these cyclic variables, they have a distinguished meaning because they lead to conserved momenta. Yeah? And in classical mechanics, when we discuss the so-called Kepler problems or the classic motion of planets, we made use of these cyclic variables, and the same will happen here, in fact. So these here are the cyclic variables, and you will see that they lead to conserved quantities, and I can already, of course, tell you now because it's similar to classical mechanics, so this will be related to energy and this will be related to angular momentum, and you make use of the two to reduce the problem significantly and make it treatable. How does it work in detail? Now, we have this t, phi, theta, and r, and we discuss them in this order. So let me first then discuss the Euler-Lagrange equation for t. No? So Euler-Lagrange equation reads. Now this is the standard form for mechanics. You have d over d lambda, dl dk over dt dot minus dk over dt is equal to 0. Now, this is what you get from such a variational principle, and I'm sure I don't have to repeat this here. Now, because t is cyclic, it means that k does not depend on t explicitly, so this is 0, and then you see the conserved momentum. I mean, the dk over dt dot is the momentum, and d over d lambda of this is 0, and this is a conservation law. So dk over dt dot, I mean, it's easy to calculate. To differentiate this is minus 2 e to the nu t dot. So from this then you get that e to the nu t dot is a constant. It does not depend on lambda. D over d lambda of this is 0. And let me call this constant, this conserved quantity f. It's dimensionless, a dimensionless quantity here, and we will interpret it now, its meaning. What is the interpretation of f? Now, let us recall here the meaning of conservation in relativity. We have related this to so-called symmetries described by a killing field. Now, we have a killing field here that is connected with t and, of course, also with phi. So, because here, again, that's another name for the cyclic nature of these variables. So, we have the killing vector field connected with t, and so this killing field, if you go into a particular coordinate system, actually the coordinate system written down here, where the metric does not depend on t explicitly, this is why I denote this by a star, it's an equation that is valid in a particular coordinate system, then it's just 1, 0, 0, 0. It's just the vector that points in the t direction. And you have learned in part 1 of the lecture course that g mu nu, u mu psi nu is constant along geodesics, where this is the tangent vector of the geodesics, so dx mu over d lambda, and this is of course the killing field along geodesics. So let us consider this conserved quantity. So minus g mu nu u mu psi mu, which we can also write as a scalar product. So this is the same as the scalar product between the two 4 vectors. I mean the 4 velocity, or well, the tangent vector and this killing vector. And it's clear if we go to this particular coordinate system. So then this is minus g 0, 0, u 0, psi 0, because this is the only non-vanishing component, and we only have diagonal components here. So this here is a minus e to the nu, as you can read off there. The u 0 is dt over d lambda, which is the same as t dot. And of course this is 1. You directly see that this is 1, so this is e to the nu t dot. And if you look here, this is just our f. So this is just our f. So this conserved quantity is the quantity that you get from the scalar product of the tangent vector with the killing vector. If you go to standard Schwarzschild coordinates, then just you have to insert here with the 1 minus 2 gm over r. So this here is in standard Schwarzschild coordinate. Uh, 1 minus 2 gm over r times t dot. So in flat space-time it would just be the t dot, which would be somehow the lapse of the coordinate time with respect to proper time, or with respect to the affine parameter. This I have not yet shown you that f in fact is related to the energy of a test particle. Let us do this here. So the energy of a test particle. Well, test particle is, of course, how a particle physicist would call it. I mean, we talk about the motion of planets, and so a planet in this sense is also a test particle. It means that the gravitational field of the planets is neglected compared to the central gravitational field. We just have the motion in a gravitational field. of another body. So the energy of a test particle, let me call it epsilon, is minus p u observer. So what's that? So I mean, that's the relation you know from special relativity already. I mean, the 4 momentum of the test particle, and this is the 4 velocity of an observer. So if the observer is at rest, then you have just here the 0 component. Yeah, you can, and p is m times u. Now, if you have a massive body, and this is what I consider now, then it's m times u. So that's the 4 velocity of an observer, and this is the 4 momentum of the particle. Now this is why I added here observer here. So let me just proceed here. So far away from the body with mass m, we can just pretend that we are in special relativity. So we have the metric -1, 1, 1, 1. So far away from the body with mass m, and far away from the sun. In our case, now we have for the energy, let me call it epsilon infinity, which is then m times u 0. I mean, I add u observer here, just 1, 0, 0, 0, and this is m times dt over d lambda. So as in special relativity, and m times u0 is of course p0 infinity, and we call this epsilon infinity. Now let me distinguish between the time-like and the light-like case. Of course, this already has alluded here to the time-like case, but now let me be more specific. So let me first have here k is -1, so this is the time-like case. And so there we have lambda is equal to the proper time. Epsilon infinity is m times t dot, which is m times dt over ds. And for r to infinity, we have that our f, which is e to the nu t dot, okay, this is equal to 1 for r to infinity, because we have here the situation that, if you recall, 1 minus 2 gm over r, for example, that far away, or if you're far away from the mass, then you cannot distinguish it anymore from the flat space-time. So this means that f is the same as epsilon infinity over m. No? So you see our f, our constant of motion, coincides with the energy of the test particle at spatial infinity divided by the mass. So it's a dimensionless quantity. Now f is conserved. Yeah? This is what we have seen here. F is conserved, but epsilon is not. F is conserved and coincides with epsilon infinity over m, but epsilon is not. Epsilon receives what you might call a redshift factor. Well, the word redshift refers to the photon case, which I discuss later. But anyway, it receives a redshift factor. So note that psi times p, the killing vector or minus, is constant, because this is m times u. And in that particular coordinate system, we have minus g00 times p0, which, if this is evaluated at infinity, at r to infinity, is p0 infinity, which is epsilon infinity. So we also have for the observer, I mean that g mu nu, u mu observer, u nu observer is -1. Now this here is a minus e to the nu. So from this, you get that u0 observer is e to the minus nu over 2. I mean, if we assume the observer at rest, so that the observer only has a temporal component. No? So observer at rest, u mu observer is, in that particular coordinate, 0, 0, 0, 0. Now the energy epsilon is minus g mu nu times p mu times u nu observer. Now this is what we had earlier on, and so in the particular coordinate system, this is minus g mu 0 times p mu u0 observer, which is minus g 0, 0 p 0 u0 observer. So this here is e to the mu, and this here, as we have seen here, is e to the minus nu over 2. So we get e to the nu over 2 times p0, and p0 is e to the mu times e to the nu times epsilon infinity, so which is e to the minus nu over 2 times epsilon infinity. Now, so this energy, the energy of the test particle, E, is then related to the energy it has at infinity by this factor e to the minus nu over 2. No? So let me write this again separately. Epsilon is e to the minus nu over r over 2, epsilon infinity, which in standard Schwarzschild coordinates is 1 minus 2 gm over r to the minus 1/2 epsilon to infinity. And this is, you see, then what we call the redshift factor. I mean, in the case of the photon, it would correspond to redshift. Here, in the case of a planet, it's just a factor that relates the energy. No? The energy at infinity, as you see, is less than the energy it has at a finite radius r. And this is why we call it a redshift factor. Yeah. Okay, now I have to erase and then do the photon. We have, in case 1, treated the time-like case, and let us treat now the light-like case, where the value of the Lagrange function k is 0. So this is the light-like case. So here, lambda is of course not a proper time, as emphasized many times, but it's an affine parameter along the light ray. There is no proper time for light. Now, we have the same expressions. Epsilon is minus g mu nu, p mu, u nu observer. And of course, if we have photons, say, we can, of course, anticipate that they are quantum objects, so the energy can be written as h bar omega of r. And so that's a difference now to the case 1, that we can do that here, so we can relate this to the frequency. And so we have here, this is equal to, in that particular coordinate system, at infinity to p0 infinity. So this is for r to infinity, which is the same as epsilon infinity, and this is minus psi times p. And this again we can relate to an energy quantum frequency h bar omega infinity. So if we are at finite r, then we have, as before, epsilon is e to the minus nu over 2 epsilon infinity. If we use now here this relation with the frequency, then we can write omega of r is e to the minus nu over 2 omega infinity. Or if I insert here the expression for the standard Schwarzschild coordinates, it is 1 minus 2 gm over r to the minus 1/2 times omega infinity. No? And then you see here explicitly that omega infinity is smaller than any omega at finite value. That is, the photon has suffered a redshift when climbing from a finite value to infinity. Of course, this is what we discussed already in section 9.1, no? When you had the static situation, a static gravitational field, and you emit a photon to a certain height. So that's here then the redshift, so the gravitational redshift. Or if I draw a small diagram, a coordinate diagram, so we have here t and r, and we have here the Schwarzschild radius. Of course, this is inside the spherical body. So that's a region that is not of interest here, will be of interest later. And we have here r, and here say r to infinity. Then we can have here the emission and the absorption, so emission, and here the receiver. And so we have here the frequency omega of r, and here we have the frequency omega to infinity. No? So when you emit that photon from that finite height r to infinity, then you get a redshift. And you can calculate it by this means, and whenever you have another metric and you have a killing vector field, you can do the similar calculation, and you get the correct result, as we did in the section 9.1. Now, so far for the time component of the Euler-Lagrange equation, we have three other coordinates, so let us go through them. So the next is the phi coordinate, the azimuthal angle, so phi, and as anticipated, it also leads to a conserved quantity, namely the Euler-Lagrange equation is d over d lambda, dk over d phi dot is 0, because dk over d phi is 0, and so if you insert the k, which I wrote down earlier, then you get that dk over d phi dot. It has that explicit form e2 r squared e to the mu sine squared theta times phi dot. That this is constant, because its derivative is 0, and let me call this constant 2L. L again is dimensionless. Now, you know that we have a second killing vector, because the metric does not, in these coordinates, explicitly depend on phi. And this is an axial killing vector, eta mu, which in these coordinates has the expression that it just points to the phi direction. So, and we have the conserved quantity, that g mu nu, times the tangent vector mu times the killing vector is a constant, which is here given that when this is the 0 component, 1, 2, that's 3 components, so this is G33 U3, and if you insert G33, this is R squared e to the mu sine squared theta times U3. And U3 is, of course, d phi over d lambda, which is the same as phi dot. Now, if you compare it to this expression here, then you see that this is just the L here. So this is just the L. No? So the conserved quantity related to the axial killing vector is that small l, and you will see in a moment that this is can be interpreted as the angular momentum of that test particle per unit mass, so that it becomes dimensionless. Now, so I can write it already here, angular momentum per unit mass. No? So you see we have two Killing vectors and associated with them two constant of motion, which we call F and L. So these are constants of motion associated with the symmetries of the Schwarzschild metric. Associated with the symmetries of the Schwarzschild metric. The next coordinate is theta, and theta has a theta dot in the Lagrange function, but also theta occurs explicitly in the sine and cosine theta. So it's no longer cyclic. So theta, then we have the following Euler-Lagrange equation. You have d over d lambda dk over d theta dot minus dk over d theta is 0. And now we have a non-vanishing value here. This is easy to calculate given the explicit form of k. So this is here 2r squared e to the mu theta dot. And this here is 2r squared e to the mu sine theta times cosine theta times phi dot squared. Yeah, and you can differentiate this and so on. That's simple. And what you get here is that you have r squared e to the mu dot times theta dot plus r squared e to the mu theta double dot is r squared e to the mu sine theta cosine theta phi dot squared. So that's what you get. Of course, you have here the highest derivative, the theta double dot, and you have theta dot terms, and you have other terms. Now, this is, of course, as usual, second order equation. So you need two initial conditions to fix a solution. So, which means that we fix initial angle theta and initial change of angle theta dot. And of course, we choose it simple. So let us choose the initial conditions as follows. That we have theta is theta is pi over 2, and theta dot is 0. So this means if initially theta is pi over 2, that this here, the right-hand side, is 0 because of this vanishing here. And theta dot equals 0 means that initially this is 0, which means that also this here is 0 initially, and the whole trajectory stays within the plane theta pi over 2. So then we have here that r squared e to the mu theta double dot at initially, say initial time 0 is 0, and from this we have that theta double dot, because this is non-negative, initially is 0, which means that the whole trajectory lies in the plane, in the coordinate plane theta is pi over 2, as in classical mechanics. Now you know that from the Kepler problem that the motion of the planets is restricted to a plane around the sun. The plane. So as in classical mechanics, So there's no change here. Now we can always set then theta equals to pi over 2, which means that we have for our L, if you recall, L has this value, that L is r squared e to the mu sine squared theta phi dot. And of course, if theta is always pi over 2, so this is equal to 1. So L is e to the mu r squared phi dot. that's the constant quantity. Now, if you look at the angular momentum in classical mechanics, we have the following well-known expression. So angular momentum in classical mechanics. Let me call it LC, L classic. So this is m r squared d phi over dt. No? R cos p, and this is what you get in polar coordinates, which means that if you divide it by the mass, you just have r squared d phi over dt. Now you have to compare the two here, this expression and this expression. Of course, they are not the same, but they coincide at a spatial infinity. Why? I mean, at spatial infinity, e to the mu goes to 1. And here you have, say, for a massive particle, d phi over d proper time, but at spatial infinity, this coincides with coordinate time. No? So they coincide at infinity. So expressions coincide at r to infinity. Now, this is why we can interpret a small l as the angular momentum per unit mass. So the final coordinate that we have to address is the radial coordinate r. Of course, we could do a separate variation, but actually it's not needed. Why? Because we already know that k equals constant is an integral of the equation of motion. I mean, we have k equals 0 for light and k equals -1 for test particles. No? So that saves us work. So here a separate variation is not needed because k equals constant is an integral of the equations of motion. No, so it's k equals 0 or k equals +1. So the k, recall, as the following form, k, and we restrict now to theta is pi over 2, no, because the orbit is restricted to there. And so this is minus e to the nu t dot squared plus e to the lambda r dot squared plus r squared e to the mu phi dot squared. No, so we know that this is a constant, and what we can do now is to replace the t dot and the phi dot by the conserved quantities, and so we have one equation left for the r dot squared and the r. So let me do this at the end of today's lecture, and let me specialize to the Schwarzschild metric and standard coordinates. So where we have e to the nu is e to the minus lambda is 1 minus 2 gm over r, and we have mu equals 0. Now, these are the standard coordinates, and we had that f, the constant of motion, is e to the nu t dot, which is then here 1 minus 2 gm over r t dot, which is constant. And we have L, which is e to the mu r squared phi dot, which here is just r squared phi dot, and which is constant. No? So you can replace the phi dot and t dot here by the conserved quantities f and L. No? So we insert this here. So the 2 here is inserted here, and this gives us then an equation that says r squared over 2, we can write in that way, plus some other terms are constant. No? So we then have that r squared up dot squared over 2 plus g m over r times k. Yeah. So I mean, of course, I multiply by appropriate factors to put it in that way, plus L squared over 2R squared minus Gm L squared over R cube is F squared plus K over 2. And of course, there is a certain reason for writing in that way, because this now has the form of an energy law as in classical mechanics, the energy law that says kinetic energy plus ineffective potential is constant. And those of you who remember classical mechanics and the Kepler problem know that such an equation is at the center of the solution of the orbital motion for the planets. And the same will happen here. So I will discuss this in detail next time, but you can already see now here old friends from classical mechanics, like the Newtonian potential, and for k equals -1 and the centrifugal potential. There's also an unknown which occurs for the first time here, which comes from relativity, an additional potential, and this is a constant. So this is the energy law divided by mass, so per unit mass, so that you have a dimensionless form, and it has the form of so energy, kinetic energy we call T in classical mechanics, plus V effective is E. So effective energy law. Of course, it has only the form of an energy law, because this is not equal to F, for example. It's F squared plus K over 2. So what we do next time is then we start with this effective energy law and then derive from it the equations of motions and their solutions. We first do it pictorially to have an idea about the qualitative behavior of the orbits, and then we go more concretely to concrete effects, for example, the perihelion motion of the planets and also the deflection of light, and see how we can derive these effects from this equation, and how we can see the important differences to classical mechanics. Of course, the important differences lie all in this one single term. Well, not for the massive case. No? For the light case, anyway, we have no effect in classical mechanics. But for the massive case, where k equals -1, I mean, we have the Newtonian potential and the centrifugal potential, and now we have this one additional new term. So, hope that you all listen then also to the next time and see this exciting topic of the motion of planets. So far for today, so bye-bye.